All right, folks, it's back in action here. We are almost done with this chapter. We've got 3 videos to go, and in these next 3 videos, we're going to look at inverses, solving with inverses, and Cramer's rule. On this video, we specifically just want to talk about inverses of a matrix, and then in the next video, we'll talk about how to use inverses to solve a system. So if you didn't like using the Gauss-Jordan method in those row operations, you might like this one better. All right, so let's start here at the top, filling in some of our blanks in our vocabulary. We've got the inverse of an n by n matrix. Now, what this should jump out to you with is that means that the rows and the columns are the same. Okay, so an n by n matrix A, that inverse is going to be noted A to the negative 1. So this is the same type of inverse notation we've used in the past for inverses, for our function inverses as well. When your matrix A is multiplied by its inverse, the product will be the identity matrix. Now, we talked about the identity matrix a couple videos ago, and you can see an identity matrix right here. So what I've got written out right here, so here's our 2 by 2 matrix. Remember, rows and columns are the same. Here is our matrix times the inverse, and then here's that identity matrix that we talked about, okay? Now, what we want to know is that only a square matrix could even have an inverse, hence, our definition that we've got up there above, where the n by n, meaning the rows and columns have to be the same. And it's also important to note that not all square matrices will have an inverse. So first of all, it has to be a square matrix, and then you're not even guaranteed that you'll have an inverse. Now, to find the inverse matrix, because we're going to need that inverse matrix, that A to the negative 1, we are going to need what's called the determinant. Now, I'm going to just give you the formula for the determinant, and I do have a proof for this here in class, or if you're watching this video and you're not one of my students and you want it, just shoot me a comment and I can get that to you if you're interested in the proof of this formula I'm going to give. So our determinant is A times D minus B times C. And what you have to know is that in this square matrix, this 2 by 2 matrix, they have specifically denoted each element, each location in the matrix as A, B, C, and D, and that matters. Now, our formula for the inverse matrix then will be, we're going to take the reciprocal of that A times D and B times minus B times C, and we're going to multiply that by a modified matrix. Now, it is very important to notice that when we distribute that scalar, that the matrix that we're going to distribute it to is not our original 2 by 2 matrix. It has been modified. Look at that very carefully. So let's jump into an example here of how this whole process would work. First thing that we would do is we would find our determinant. So remember, that formula is going to be A times D minus B times C, and then you have to remember where those are. So it's A, B, C, and D. So when I think about it, I just think this product minus this product. That means that I'm going to have a 6 times 4, and you'll certainly do some of this in your head later, minus our 10 times 3, which means we're going to have a 24 minus our 30, and that's going to give us a negative 6. So when we want to actually find the inverse, we're going to take the reciprocal of that, so a negative 1/6, and then we're going to modify the original matrix. And when we modify the original matrix, what we're going to do is we're going to flip-flop this diagonal. So those values are just going to reverse. So it's going to become a 4 and a 6. And then on the other diagonal, we're going to change the signs. They're going to stay in the same position, but their signs are going to change. So it's going to become a negative 3 and a negative 10. And then we're going to distribute our scalar. And of course, as always, we're going to reduce. So as we distribute that negative 1/6, our first element will become a negative 2/3. As always, do not convert these things to decimals. As we continue, we're going to then get a 5/3, and then we're going to get a 1/2, and a negative 1. Okay, so that is our inverse matrix. This is our A to the negative 1. Okay. Now, to understand how this actually works, because it certainly feels a little weird that this is going to give us an identity matrix when we're done, what we're going to do is we're just going to prove that for ourselves. We're going to show how that works. We're going to take our A times our A to the negative 1, which means we're going to take our original matrix, our 6, 3, 10, and 4, and we're going to multiply it times our negative 2/3, our 5/3, our 1/2, and our negative 1. So remember, when we do our matrix multiplication, I'm going to take this product. So 6 times my negative 2/3 is going to give me a negative 4. Then my 10 times my 1/2 is going to give me a 5. So I'm going to add my 5 there. Continuing, I'm going to take my 3 times my negative 2/3, and that's going to give me a negative 2. And my 4 times my 1/2 is going to give me a positive 2. You guys might feel really comfortable with your matrix multiplication by now. And then I'm going to move to the next. I'm going to take my 6 times my 5/3, and that's going to give me my 10. And then my 10 times my negative 1 is going to give me my negative 10. And then my last one will be a 5 plus a negative 4. When I clean all of that up, negative 4 plus 5 is a 1. My negative 2 and 2 is my 0. My 10 and my negative 10 is a 0. And my 5 and my negative 4 is a 1. And that's exactly what we wanted it to be. So we've now shown how to get an inverse, and then also proven that if you take the inverse times its original matrix, that you will get the identity matrix. And then in the next video, we're going to look at how to use this process to solve some systems of equations.